Okay, well, I'm very happy to welcome everybody to Matthew's dissertation defense. So it's been very interesting working with Matthew over the last several years on this very difficult set of problems that he took on. He's done a tremendous amount of implementation work backed by various abstractions to produce the first a pretty complete implementation of a programming language vision that we kind of handed to him when he walked in the door, because he said when he interviewed for the PhD that his superpower was making large code bases run. And lo and behold, he's actually done it. So Matthew came to us from Berkeley, where he did his undergrad degree in computer science. And he's been working largely on this here, but with a few papers along the way on other things. And has also served the department in various ways, including as a TA. So looking forward to hearing the talk.
All right.
Oh, and just to say a word about format. So Matthew's going to give a 1 hour talk, including questions from the audience. And so people are welcome to question or indeed challenge anything. Do you want to take questions along the way or wait till the end?
Either way, the talk will be split into kind of like 4 major components. So in the middle, if people want to, they can ask questions, but otherwise I'll take them. I plan to take them all at the end.
Got it. Okay. So you'll pause for questions a few times in the middle. And after that first hour, we'll ask the committee will ask the non-committee members to leave, and we'll do some questioning about the document as opposed to the talk. Okay. Without further ado.
Before I start, can all the remote people hear me? I don't know what the audio is there. I just want to make sure. Someone say it works.
Yeah, we can hear you.
Okay, great.
Yes.
All right, great. Thank you. Okay. So thank you everyone for coming to my PhD defense. I'm Matthew Francis-Landau, and I'm going to be talking about declarative logic programming via term rewriting with a relational algebra. So what is this talk about? This talk is about my PhD research for the last 7 years, which has been about the Dyna programming language, which has been designed for artificial intelligence and machine learning researchers. It's weighted, it does forward and backward chaining, which is a prolog and data log style execution, supports dynamic programming, memoization, higher order functions. And it was challenging to implement due to the combinations of features. In the second part of the talk, I'm going to be talking about how we can make Dyna work using a relational algebra and term rewriting. And in the third part of the talk, I'm going to be talking about some extensions that we do to our term rewriting system, which is how to use memoization and define this as a set of rewrites, and then how to compile the sequence of rewrites to make it hopefully run faster. So the Dyna project was originally started in 2003 as an extension to Datalog, which is a declarative logic programming language. And it means it can support semirings, which is really just a fancy way of saying that Dyna is good notation for dynamic programs. As such, Dyna was used for a number of different problems, such as parsing and HMLs. In 2011, Dyna 2 was proposed with a position paper about making logic programming better. It proposed features such as object-oriented programming and removed the restriction of a single semiring. It also added support for prolog-style backwards chaining, which allowed a lot more interesting problems to be implemented. In this dissertation, I also add in first-class functions and delay constraints. So the Dyna project has grown considerably over the last 20 years. So how does my research fit into this picture? Well, what we're going to do is we're going to take the Dyna language, and we're going to compile it into relational expressions, which I'm going to call RXprs for short. Using RXprs, we're going to manipulate them or rewrite them or execute them using rewriting. We're also going to represent queries against the Dyna program as RXprs, which again, we're going to manipulate using rewriting. And finally, the RXprs serve as the representation of the results, and they'll be returned to the users, hopefully in some nice format. So this bottom part of this slide here, plus some syntactic extensions, is my research, and this kind of design of the language is the prior work. Furthermore, I'm also going to be discussing memoization, which is how we can save RXprs for later reuse rather than having to recompute from scratch every time. And also, I'm going to be talking about compilation of term rewriting to make this run faster. All right. So for the first part of this talk, I'm going to just introduce dynamic and logic programming so we have a foundation to discuss from, and also motivate the research for why this is a hard problem and why we should care. So first, what is declarative programming? The program specifies what to do and not how to do it. For example, SQL databases, you might say retrieve the information about Jane, not read through a file. If the line of the file says the name Jane, then return the line. That's very procedural. A common example in programming is configuration for programs. For example, host the website for Johns Hopkins. Open port 80, accept connections. If the host name equals Johns Hopkins, read the file from the disk, right? That's very procedural. English is an example of a very declarative language, for example. So for example, you can give a high level command, clean the car. And this is sort of, I want the car clean, just in a command form. I don't say get the vacuum, point it at the rug, turn on the vacuum, and so forth. I can say make me a sandwich, which is some sort of like, I want a sandwich, give me food. Not put bread on, get bread, put lettuce on it. This is very procedural. If you're an advisor, you might just say do research. You don't say open your text editor and type in Python and then do other things. That's very low level. And in some ways, we can kind of think of robot do something, just solve AI as a sort of a declarative problem. So now what is declarative logic programming? Well, instead of just having this sort of abstract notion of declarative, we're going to have that programs are defined in terms of terms, which are just statements that are true. And terms can either be given as facts, you just assert this to the program, or terms can be deduced using rules that combine terms. So for example, here are some facts about the real world that I'm inserting. For example, Charles is James's parent, or Elizabeth is James's parent. Terms in this define a relation. In this case, we call the relation the parent relation. And how we choose to interpret this relation is up to us, the programmer. For example, Charles is James's parent, or we can have James is Charles's parent. There's just two arguments, and we don't know what the interpretation is. We can switch these, we can assign variables to them, it doesn't matter. The system will just handle it, and it's up to us to figure out that interpretation. So rules can define new terms by combining other terms. For example, we have grandparent if you have a parent of a parent. And what you have is you have these variables x and y, which is in the head of the term, or ahead of the rule on the left-hand side, and they will take on the same value as on the right-hand side. So the x and the y will have the same value in both places. Similarly, the z, which only appears on the right-hand side in the body, just needs to be filled in with some value to make this expression true. So for example, if we take Charles and James, we can fill in the first parent. And if we take James and George, we can fill in the second parent. And we can deduce that Charles is George's grandparent. Similarly, we can take the Elizabeth is James's parent and James is George's parent. And we can assert that Elizabeth is George's grandparent. Okay, so what is weighted declarative logic programming now? Well, terms have values associated or weights. Rules are now defined by expressions that compute values. So for example, we can now compute the probability that a term is true rather than just asserting something is true or false. And we don't want to necessarily, trust the facts we're given. We're going to assign probabilities, for example. So now we have the same sort of Charles is James's parent, but now we only have a 0.9 probability associated with that. We have Elizabeth is James's parent, but now with only 0.8 probability. We have the grandparent rule, which is now an expression. We are multiplying these values together, and then we are using an equals to say the grandparent is equal to this value. If we take this 0.9 and this 0.7, which is the combination of the Charles James and James is George relation, these get multiplied together, and this defines the grandparent relation with 0.63 as its value. Similarly, we can do the Elizabeth James, and now we get 0.56 as the multiplied value. Okay, so we can keep going with this, and we can define new facts into the language. We can modify the program after it's been started, for example. And now we have Sophia, our Charles is Sophia's parent. This gets multiplied together, and now we have Charles is George's parent, but now we have it twice. We have it with 0.48 and 0.63. And this is going to be an error because we don't allow this one term to have two different values. And if you write this in your program, you will get an error value back. So we need to fix this. So the way that we fix this is we have aggregators, and what aggregators do is they specify how to combine values. So for example, we have plus equals, which says that you should sum the values. And I just want to point out quickly that this sums to 1.11. We do not enforce that these values have to be probabilities. We're not a probabilistic programming language. We are just, this is a value. These are functions essentially with aggregation that combine stuff. We have different aggregators also. So for example, we have max equals, which just selects the max value. So we have the max of 0.48 and 0.63 equals 0.63. And we have different kinds of aggregators for different situations. For example, we saw the colon dash, which is the prologues, just there exists something that's true. We have plus equals and times equals, which takes the sum of all the inputs and the product of all the inputs. We have min and max, which take the min or max value of all the inputs. We have logical and logical or, so for Boolean values. We have a colon dash, which lets you override values by using the last line of the last defined line will override the previously defined lines. We have a question mark equals, which lets you just choose anything. So if you have different ways that can be computed, this will let you choose. We have equals, which requires that exactly one is contributed, otherwise it results in an error. And we also have, and you can also define other aggregators, and we have other aggregators such as concatenate list, which will just return a list in arbitrary order of all the values. Okay. So our premise is that aggregation plus logic programming equals concise programs. So for example, we can define pointwise multiplication by just saying A of I. So A with I as an argument is equal to B of I times C of I. And this gives you some value. You can also define a dot product like of a vector. So A plus equals B of I, C of I, so that I will be the same. And this is just doing the inner product where all the B's and the BI's and CI's are the same value. You can define matrix multiplication in a single line. So you have AIK plus equals BIJ times CJK, where the J will take on all possible values and they'll be equal to the summation that I'm shown here. You can also define more complicated things. For example, we can define the infinite identity matrix, where we say that if its two arguments, the II are equal to each other, then it will have a value 1. And if IJ are not equal to each other, it'll take on the value 0. This is an infinite identity. Now, if you've been following this research on the DINA project for a while, you probably have seen a lot of these examples over the years. And you're probably thinking, okay, well, these are some, the same examples that we've been showing for 13 years. But like, can we make real programs with this? What is the sort of evolution of this project? And so here I'm going to go through some a little bit more complex programs that we could write in DINA, just to kind of illustrate what the various features are. So for this example, I'm going to talk about CKY parsing, which is a probabilistic parsing. In the top right, which maybe you can't see very well from this front screen, I have a little sample input, which is Papa ate the caviar with a spoon, and this would be an array basically of values that can be passed in as the input. One thing we can do is we can define domain-specific languages. For example, we have this grammar function, which would take a string of this grammar. So we have S goes to NP, VP, or noun phrase, verb phrase, and you can embed domain-specific languages specific to your problem. So this is just trying to make the language into something usable. We have object-oriented programming. For example, the grammar function up above could return the object, and that has a function on it called rule. And that would take the argument of the word and the term. We have the ability to attach extra metadata to terms. For example, we have arg and $arg to give back the metadata, and this allows you to define things like argmax. So now instead of max equals, this will become the argmax of a particular value. We have $memo, which allows us to control the memoization policy. Basically, this is sort of a meta rule, which lets us control how the system executes, and it lets us switch between prologue style and data log style of execution. We also have inline functions or lambda functions. For example, we can use the aggregator max I for word W equals word I, and this will tell you the length of the sentence just inline, and this would print out the parse of the sentence from this program. Okay. We also have a Python API. So this is more of trying to get this into the point where people may be able to start using this. So Dyna can be imported into Python. We can run queries on the Dyna instance, and the Dyna program can be passed into the Dyna instance like you might pass a string of SQL into a database. Here on these first two lines, I've defined a new term for factorial, which is just the product of all the numbers smaller up to the n. Here's an example of concatenating to the head of the list, which is quite standard for logic programming. We can call the factorial on a number n as the first and append it to the head of the list. And here we're recursing onto the factorial list to the smaller elements of the list. We can have results from queries. We'll get cast back into some Python data type. So this can be used in Python and integrated with Python programs. So this is pretty cool. We're starting to get into a point where we might actually be able to start using this language. So the next question that I want to address is, why is this hard? I mean, people have been in programming languages for a long time. And the answer is that Dyna has a combination of features that are interesting due to their intersection. And for example, Dyna's out-of-order execution simplifies writing programs, but it complicates Dyna's implementation, which will be what I talk about next and for most of the rest of this talk. Okay, so let's just go through quickly and compare what Dyna's features are versus some of the prior work. At the top of this table, I have SQL, which is SQL databases, data log, prolog, constraint logic programming, probabilistic programming, Dyna 1.0, and Dyna 2.0, which is the work that's in this dissertation. So first we have finite, which is supported by all strategies, and it terminates because you can just loop over the entire database and you're guaranteed termination. Next we have deductive, that you can define rules which combine facts to infer new facts. You can have infinite relations. For example, can you define the set of all positive integers, or can you define the set of prime numbers? Can you do weighted? Can you associate values with this? So for example, the logic programming, they're only true or false. You can't associate values very easily. And Dyna and probabilistic programming examples are able to do that. Aggregation, for example, can you compute aggregate statistics of some value, so the sum of some particular column. Materialized or memoized intermediate results. So this is important for some algorithms to get the appropriate performance. So Prolog and constraint logic programming usually do not have this. Turing complete, or basically is this some sort of full programming language or some sort of small subset? Constraints. So for example, if I have x less than y and y less than x, are you able to identify that there's no value of x and y that satisfies this expression? Do you have object-oriented programming, which I showed with that little dot? And then syntactic sugar, basically, this doesn't necessarily make the implementation too much harder, but it's just sort of a nice to have thing. And of course, in Dyna, we want to have all of these things, which has some hard to mix combinations. For example, if you have infinite relations in aggregation, this is hard to mix. For example, you can define an infinite sum. You can say, I want to memoize. You can have hard to mix between memoization and constraints. For example, memoize the set of all integers greater than or equal to the number 4. You can have infinite relations in objects. So usually when you're writing a program, you think of an object, it gets allocated in memory. You could conceptually write a program which says allocate an infinite number of objects. This is doesn't really work for us. All right, so what are some example programs quickly of these hard programs? So for example, here's a simple program which is going to create a new object. And this is defined for all floating point values x. And what we can do is we can say, compute the argmin of x over all possible x's. And this is just using the min aggregator and the arg and $arg. Now, conceptually, this program is actually quite simple if you can represent this program and you can not get tripped up over the fact that you're quote unquote allocating objects. You can have some sort of call out to some sort of convex optimizer or linear program to solve this, or a quadratic program, not linear program. Another example of this is a quote unquote infinite neural network. So what we can do is we can define a nonlinear sigmoid function in Dyna. This is just over any floating point values. And here we've defined the neural network as a edge between nodes in a graph, which is a little bit weird for the way people usually define it, but this is conceptually something we could do in Dyna. And then we can define rules which define the edges. And here we have, for example, an edge rule, which defines an infinite number of edges. For example, we have input of 510 can have an edge between that and hidden 1120, but we can also have input 500 and 712 to hidden 503 and 709. So there's an infinite number of these edges. Now you can actually run this program, but what you have to do is you have to have some sort of finite input, and then the program is only going to instantiate the graph on that finite input. But that means that you have to create a large enough understanding or large enough context of the program such that you're able to execute this correctly. All right, so I'm going to now get on to the relational expressions part about how we make this work. Are there any questions briefly? All right. And this is the second part of this diagram of where we go from Dyna down to RXpers and term writing. So to illustrate relational expressions, I'm going to start with the shortest path program just because it's simple and it's got a little bit of enough interesting behavior in it that we can see what's going on. So again, we have variables that are not present in the head, such as this X variable, are going to be aggregated over with the min aggregator. And this is only going to keep the min value that we've computed. This little shortest path program is going to be computed with some edge facts, which are the distance between nodes in the graph, such as a distance of 10 between the edges A and B, or 2 distance between B and C. We can think of the Dyna program as being equivalent to the set of values that are defined. For example, we can see that between node A and node D, there's a distance of 19, which would be going from A to B, B to C, and C to D, which is the sum of 10, 2, and 7. This program, we have this start is min 0, which is in this case defined for all arguments where the arguments are equal. So for example, foo, which was not in our graph, but it's just defined 7, pi, so on and so forth. So this is a little bit of a challenge for something we can handle, but it's challenging for many other logic programming languages. So let's start working on this translation. So we have distance SS equals 0, and I'm going to bring back aggregation later, but for now we're just going to look at equals. And we can think of this as being equivalent to the set of tuples where we have three variables such as R1, R2, and result. And we have some executable code which defines the rule. In this case, R1 and R2 should be equal to each other and result is equal to 0. And then we can try to do the same thing where we have S for the recursive rule. However, because of the recursion, we can't quite write this in the set builder notation because it needs to reference itself. So we're going to start again, and we're going to try something else with this second rule. So first step we're going to do is we're going to normalize with a standard name. So we're going to say distance of R1, R2, and result. So all calls will have the last variable will just be the result of whatever that is, of whatever that call is. And the first thing we're going to do is we're going to have an RXpr call the function by name. We have intermediate variables being introduced for the result of the edge, for example. We have a recursive call to distance, which now we can reference. And we can have built-in such as plus, which are also getting represented as RXprs. We can take the intersection of these, and by the way, all these things at the bottom are RXprs. And we're going to, by intersecting the bag by multiplying the multiplicities of these expressions, as we'll see a lot more. Now, this expression is over the tuple R1, R2 results ED and X because all those variables are present in this RXpr. And what we can do is we can project out the local variables ED and X, and now we're going to have a tuple only over R1, R2, and result, which is what we want. So how are we going to represent aggregation? Well, we're going to represent this in the RXpr. And what we're going to do is we're going to take the RXpr, like the one we defined on the previous slide. We're going to have an intermediate variable, which is the input to the aggregator, just like in the case of projection. And we're going to have a result variable for where the result of aggregation is stored. Okay, so now we're going to put this all together and we're going to build the entire RXpr. So we have distance R1, R2, and result. So both of these have the same normalized argument names for both rules which define this term. We start with R1 equals R2 intersected with the minimum input is 0. And we have this projection expression, which is the same one that we saw from 2 slides ago. We're going to take the union of these two things, and then we're going to wrap it in an aggregator. And this is the complete this complete definition represented as an R expert. Okay, so now what do we do with this once we have this definition? Well, we're going to manipulate these using rewrites. And all our rewrites are semantic preserving, and they will attempt to simplify the expression. They're non-deterministic. We allow any order of rewrites to be is acceptable. And we will look for a sub R expert in a larger R expert expression and attempt to rewrite it. And this requires that we search through the entire big R expert tree to identify what can be rewritten as run, as we'll see throughout this talk. And we have a requirement that rewrites need to be fair, so that if there is some rewrite out there's some chance that it eventually gets applied. And this is important in the case of recursive programs. Otherwise, you can get starvation. So what are some rewrites in the case of user definitions, just to warm up with? So we have the distance arg1, arg2 as a result, and we're going to write rewrites as this arrow. And it rewrites as another semantically equivalent R expert. In this case, this is the R expert that we previously constructed. We also can have the edge facts, and this is going to rewrite as edge arg1, arg2, and we just have this result only. This first line goes over here. So we have arg1 is A, arg2 B, and input is 10. And note that we always have an aggregator when we do this translation from Dyna. In this case, the aggregator only corresponds with the equal and enforces that only one of these is allowed to be true at a time. All right. So we're going to now look at some rewrites on built-in operations like the built-in plus. Now, conceptually, a built-in plus is semantically equivalent to the tuple. The bag of tuples where the assignment is the sum of the first two arguments is the sum of the third. So we have 1, 2, 3, and 4, 5, 11 as examples. Semantically, the definition is that if X and Y equals Z, then it's 1 and it will be 0 otherwise. We can embed values into these tuple expressions, in which case then this is equivalent to a tuple over 1 bag where we have 1, 2 equals Z. We can then do a rewrite on this where we get Z equals 3, and this is equivalent bag. And the semantic definition of this expression is just that the variable Z must take on the value that's assigned in this assignment expression. All right. So if we have two variables, there are no rewrites available, and this just gets left alone and stays in the R expert. And the reason is that there's an infinite number of ways this could rewrite. For example, Y equals 1, Z equals 2, Y equals 2, Z equals 3, and so on. If we have a star, which is a conjunction between two sub-R experts, we can propagate the value of using Z into this sub-R expert for built-in plus. And note that the semantics of the sub-R expert is not necessarily preserved. However, the semantics of the entire R expert is preserved. We can then do rewrites on this built-in plus because two of its arguments are known. In this case, we're computing the value for Y by doing 3 minus 1. And R experts are semantically equivalent to their semantic interpretation. For example, once all the arguments are known, it just rewrites as 1. If we have, so 1 plus 2 equals 3, but 1 plus 2 does not equal 4, so that rewrites as 0. Okay.
Do you want to make any connection between this and constraint logic programming for people who know that?
Let's just discuss that in questioning. Okay. So let's go through an example of rewriting the distance with A and B, and we're going to have a variable called distance, which is the return value. So here we take the program, which is the definition of this distance rule, and we do this rewrite, and we're going to fill in the value of R1 and R2 with the new variables A, string B, and the distance variable. We can then use rewrite rules. For example, A does not equal C, so that just is going to rewrite as 0. We have 0 times any R expert is 0, and we have 0 plus R is just going to equal that R expert. We keep rewriting and we get this new R expert. Now we can use the edge rule where we have, which is the same definition that we saw earlier. We're going to embed this. And now we have a bunch of equality checks. Again, C does not equal A, but we have C equals C, so that rewrites as 1. And we have multiplicative identity, 1 times R equals R. So we're able to eliminate the 1 from the R expert. Now we have this R expert shown on the screen. And now we can do propagation of values. So now we have the new call to where X has been replaced with the string D, and we have also removed it from the projection. So that was an example of just how this process works, and this would just keep going. But at some point, this will also get to the aggregator and needs to run the aggregator. So how does the aggregator work? Well, if you have the Rx for result equals min input, and then you have a single assignment min input equals 789, then this will just result right as result equals 789. You also have that this first example is actually a rewrite of a more general rule where if there's any variable or any value, this can also do this exact same rewrite. If there are no inputs to the aggregator, then it just rewrites as a 0 empty bad. And in the case that we have a disjunction over multiple contributive values, this is going to rewrite such according to the aggregator. In this case, it's going to take the min value. Now, this particular example is also a case of a more general rewrite rule. Let's go through this more general rewrite rule and actually see how it works. So first, we're going to take this rule. We're going to substitute in min input 1, 2, 3, and 4, 5, 6 into the R and S. And we have a rewrite rule which allows us to ignore this input is null. Which is, there's lots of details in the dissertation about this, but for now, we're just going to ignore it mostly. At this point, we can rewrite these two aggregators as MR equals 1, 2, 3 and MS as 4, 5, 6, which were the intermediate variables from the smaller aggregators. We can then keep doing rewrites on this. We can do propagation into built-in min 1, 2, 3, 4, 5, 6. We can then evaluate the built-in min, getting a result is 1, 2, 3. And we can keep going, and now we get that result is 1, 2, 3 by doing various rewrites on the projections to eliminate the unnecessary projections and evaluating the not equals. Okay, so that was the second part of the talk about introduction to R-expers. Are there any questions on this? All right. For this third part of the talk, I'm going to be talking about some of our extensions to the R-expert rewriting, and this builds on a lot of the material. This is pretty late in the dissertation, but I think these are some of the more interesting, more novel contributions of the dissertation itself, which is why I'm choosing to include them in the talk. So we have memoization, which is going to save R-experts and cache them for later readers. So before we get into memoization with R-experts, I'm going to start with kind of a high level understanding to get everyone on the same page about like what memoization is. And so what it is we save the result of the computation to avoid redoing the same computation multiple times. This is necessary for some programs to be efficient, for example, in the case of dynamic programming. So what is required to implement memoization? Well, we need to intercept calls to computation. We need to store the results of computation somewhere. And then we need to reuse the result of a memo that was previously computed. Okay, so I'm going to illustrate this with using the Fibonacci sequence, and this is a recursive program that calls itself on this last line of this Python program, and it takes an exponential time without memoization. And there's also its math definition. So how do we introduce memoization to this? Well, we're first going to override the function by redefining fib. So now we're intercepting function calls to the fib. We're going to make a global place to store this, which in this case is just a hash map or dictionary in Python. Before we call or do any computation, we're going to check in our global data structure if the value has previously been computed. And if it has, we're going to return that from the data structure rather than trying to redo the computation. And if the computation hasn't been done, we're going to call the original definition, and we're going to also save the result of the computation after it's been done for future use. Okay, so this is kind of a high-level idea of how to introduce memoization. So what does this look like as rewrite rules? So the central idea here is that we're going to be using if expressions. So here we have that we can take any R-expert, and I mean literally any R-expert can be used here, and we can rewrite it as an if expression. And what an if expression does is it switches between two R-experts. So the first R-expert here is the conditional, which is going to tell us what to switch between. The second one is the true branch, and the third one is the false branch. And note this if expression returns the same R-expert regardless of what the conditional Q in this case. And that means that these two expressions, or these two R-experts on the either side of this left right arrow are semantically the same. So what we can do is we can perform a computation on the true branch. And the way we do that is we take the conditional Q and we add it to the true branch under some conditions on Q that it's a constraint and its multiplicity is less than or equal to 1. And then once we've done that, we have Q times R can be rewritten to Q with computation done. And then I'll show this with an example in a little bit about what exactly is going on. If the conditional is rewritten as 0, then we interpret the 0 as false, and we're going to return the false branch, which is the last argument. And if the conditional rewrites as a value that is strictly greater than 0, which can be expressed using m plus q, for m is some integer that's greater than or equal to 1, then we will return the true branch. And also the conditional is allowed to read and write, or not write, but read from the environment by bringing in copies of conjunctive RxVers such as this T here. So let's go through an example of how memoization works. So we have a built-in plus XYZ, which is the RxVer that we're going to add memoization to. And in general, this might be a more complicated function than just addition. We're going to add an if expression where we have the conditional Q, and this can be chosen to be any RxVer, as discussed previously. So in this case, we're just going to memorize 2 plus 3. We can copy in the conditional into the true branch. We can then do rewrites on the true branch. So now that we have evaluated the built-in plus, so now we just have z equals 5 using the rewrites that we previously saw. All right, so how do we access the memo once we have this representation? So here we're going to have a query against the RxVer for the memo. In this case, we have x equals 2 and y equals 3. So this is going to match with the memo. This allows us to rewrite the conditional as 1 because we can factor out that t. And this means that we can return the true branch, which contains the memo, and duplicate equality assignments can be eliminated also. So what happens if we make a query against this expression where it doesn't match the memoized RxVer? Well, we have that the conditional rewrites as 0 because y equals 7 times y equals 3 is not compatible with each other. So this rewrites as 0. So now we get the false branch, and which we perform is the original computation, and then we can then perform further rewriting, which gets us a true value but skips the memo. So what is memoization in Diam?
Sorry, just to finish that example, you might then go and modify the if expression to put that result back into the.
You can modify the if expression or make nested if expressions to grow the memos as time goes on. So the if expressions are the core construction that enable memoization in a term rewriting system. And the if expressions can be introduced out anywhere. And being clever about where to introduce an if expression is critical for making the memos quote unquote work. If we introduce the memos into the user definition, they can be reused multiple times and allow us to intercept calls to user-defined functions. And also, I'm just going to mention this, but I'm not going to really present it in this talk too much, is that memos are also reactive, and so that if the program changes, the memos will also get notifications and get recomputed. But this is more just the standard reactive implementation as far as things go. So how do we add a memo to the original definition of distance? Well, here we have this original rewrite rule, and we can add this if expression here, where again, the conditional if is what we're going to memorize, which is conditioned on the arguments. And the true branch is computed by doing rewrites and then saving that into this true branch here. And the false branch contains the fallback to the original RxVer. Right. So this is going to be the last idea of this talk, and that's to extend RxVer with compilation to try and make things run faster. Are there any questions on memo? Okay.
Actually, I will ask a question for the sake of the audience. So in the dissertation, you talked about how this is more flexible than classical memoization, and maybe it's worth saying a word about that.
Yeah, so this conditional Q can be any RxVer. So for example, you could put like less than 5 as Q, and then it doesn't actually have to be just assignments to ground values. So you can have Q be greater than or equal to 4, which is the hard example of mixing memos with arbitrary constraints.
Yeah, so I think there's actually 2 parts that you talked about in the dissertation. So you might say something like, just changing your example slightly, if x is greater than 0, then the result is always 7. But you could also say if x is greater than 0, the result is always x squared. So the test for whether it's in the memo table is not exact match, and the result of the memo table is not a constant.
The value contained in the memo table is allowed to be any R-expert, which means that there can be unevaluated computation in the memo table. It doesn't have to be just the value 5 or something. And the condition on that can be an arbitrary R-expert also, so you can say greater than 5 or less than 0 or something, not just the number 0, which is more typical of memoization. So yeah, this is more powerful things. Any other questions? All right, I'm going to get on to the last topic of this, which is compilation of sequences of rewrites. So how do we run programs that are represented as R-expers? So an R-expert represents a program that is as a large tree data structure. And we're going to search through the entire tree looking for opportunities to rewrite, which is what I already said. So what are the challenges of this? Well, finding applicable rewrites requires searching through a large tree data structure. This isn't great. Some rewrites require finding conjunctions of 2 or more R-experts to match, which is potentially expensive. We have other operations that we have to do to maintain the tree, such as variable renaming, which requires recursive rewriting of a large tree data structure, again, expensive. So how can we make R-expert rewriting more efficient? We can combine multiple R-experts together to make new synthetic R-experts, and this will limit the number of distinct nodes in the tree. It also means that we can do multiple matches, can be performed simultaneously, because we're going to have a larger single R-expert that corresponds with many smaller R-experts, as we'll see. We can then generate new rewrites for these synthetic rewrite R-experts, and this will allow us to avoid the overhead of dispatching rewrites, as well as pass intermediate values between rewrites in a single block of code without having to materialize that somehow in a data structure. And we also are, given this design, required to create rewrites because these quote unquote synthetic R-experts do not have any rewrites when they're created. So this is sort of a secondary. So these two mechanisms work together. So what are the mechanisms? We're going to go through a simple example just to kind of see what this is. So imagine that we're starting with a simple user's program. So we have f of 2 arguments, x and y equals 3 times x plus g of y. And we can convert this into an R-expert. And in this case, I've drawn the R-expert as a tree data structure just to kind of illustrate better what's going on. So we have a projective temp1, temp2, which are some intermediate values on the multiplication, and the plus being all represented in this tree, as well as the call to G. Use the G. We can then combine this into a new new synthetic R-expert, which I call state 687, where it has the arguments x result temp2, but we have a call to the other G term. We can then take this state 687 and it can get composed into a larger R expression tree. And we can have operations such as, and then one thing that can happen in this larger tree now is that we can have the variable x is assigned 7, which allows us to then rewrite this times 3 times x expression inside the tree. And then we can then generate a rewrite, which will generate a new state. And inside of this new state, we're going to save the results of this multiplication because we still need access to that for other R-experts that are in state 568. So how do we make this work? How do we make compilation of rewrites work? So first, we're going to define all rewrites in R-expert types in such a way that we can get access to their definitions. And the way we do this is using Clojure, which is a Lisp-like language, and it has macros, which is really the key thing that we need. And so here's a simple rewrite that you could find in the implementation. So we have this macro called def rewrite, which defines a rewrite. There's a match statement, which specifies the R-expert to match against. There's preconditions on this match expression, such as that the variable a and b must be ground. So for example, if this times 3 and 7 would be ground values. And then this final bit is some little bit of Clojure code, and this can be any Clojure code, but this is what's going to actually do the computation. So you have get the value of the a variable, get the value of the b variable, and to compute the multiplication. And then this assigns to the variable c. And then we're going to use abstract interpretation to convert from the rewrite source code into a representation that we can compile. And then we're going to combine rewrites together to share redundant computation and matching. So this is an example of what a generated rewrite looks like, and I'm going to go through this just so don't worry too much. So the first thing is that we have some initial state that represents the macro R-expert, and this can have lots of this represents lots of smaller R-experts together. We have preconditions that check if the first rewrite matches. If a rewrite does not match, then it just goes back to the initial state here. We're then going to do a rewrite. Once all the preconditions for a rewrite have matched, then we're going to do that rewrite. And after the first rewrite is complete, there can be more preconditions to match for secondary states. Note that after we've done a rewrite, the state of the R-expert has changed. So now we're going to, if the precondition fails, we're going to redirect to a different state, such as state 32 down here. And these new states can be generated lazily. So this state would be generated at the same time as this rewrite would and not a moment before. The rewrites themselves are also going to be generated lazily and on demand. Some of the speedups that we're going to get here is that preconditions that can be resolved statically do not actually need to generate any runtime code. And this can be because the rewrite was already previously checked or because it's consuming the output of a previous rewrite. So once you get all these states and rewrites between these states, the kind of idea of what you're going to get is you have this initial state and rewrites that transition between them, as well as some sort of check failures, which happen if one of your preconditions fails and you've entered different rewrites. These states are also reentrant, which is how we're going to get reuse of rewrites or reuse of code by re-entering through states. Okay, so any questions about that? All right. So in conclusion, the term rewriting approach presented in this dissertation is the first approach that we have found that can implement Dyna. Term rewriting in relational algebras for declarative logic program has been scarcely studied before. There are a few papers, but I think this is probably one of the more extensive documents out there about that. This dissertation presents hundreds of rewrite rules and includes an implementation of rewrites. We investigate memoization and reactive updates for relational algebra, and we also make a term rewriting to run faster versus JIT compilation. So the current state of Dyna is that there does exist an implementation, and there will be some code released soon. I would also just note is that the implementation is at the level of kind of an academic prototype. We're not really able to handle real world problems set, unfortunately. And there's also lots of opportunities for future work. I discussed around 20, I think, in the dissertation. So thank you. That's my talk. Here's some cute animals.
Okay, well, thanks very much. So we've got a little over 10 minutes for questions, I guess. I see claps and confetti horns on the screen. One of them live action.
Gentlemen, so you just mentioned it's not quite ready for real world problems. We saw all sorts of great stuff.
Yeah.
To make it better. But what does it do right now in a real world problem?
So it's just that there's some places where it's asymptotically not going to give you the right runtime due to just like some data structures don't have the right optimizations in place. There's also
And does that cause it to actually get really annoying and have you pounding your keyboard? I mean, that in the end, I don't care if it's, n cubed or whatever, as long as I'm not pounding my fist on the table in disgust while it's because it's not terminating.
It does the right thing with like termination, but I mean, short of like whatever bugs might exist, but like conceptually it does that. But it's just like several orders of magnitude too slow for the kinds of problems that we want to actually solve.
Okay, so it could be that you have to wait like hours when it could be minutes.
I mean, the thing is if you're a machine learning researcher and you're going to make a program that's going to run for 24 hours, but then you write it in Dyna and it takes 1,000 days.
Yeah, right, yeah.
No, that's not.
Well,
Okay.
how much of that though is, like suppose you extended the built-ins as you suggested doing in your future work section. So they're not just things like integers as you showed here, but also include tensors.
Yeah, that could,
And so you're not doing operations at the level of tensor elements, but you're synthesizing a computation graph over.
yeah, so the set of built-ins could be extended such that you're using higher level operations, like tensors. You're probably not to GPUs in the case of like neural networks. That would certainly mean that you're spending less time dealing with the slowness of Dyna and more time just like doing math computation. But I don't know, that doesn't necessarily give you the kind of seamless sort of behavior. You're just kind of like Python with a different syntax or Python neural net libraries with a different syntax at that point. So I mean, yes, this is possible, and you know.
Well, would it go from being orders of magnitude slow to being a couple times slow?
I mean, if you spend 99.9% of your time in CUDA calls to tensors, then you're not spending your time in Dyna, so you don't care about how fast it is as much.
I mean, that's why people can use Python for machine learning.
That is why people use, yeah. So that could be a path forward for Dyna. It is an option. I have done none of that work yet. That's entirely future work.
I have a questioner.
Can unmute and just,
So you were showing towards the end a timeline of the rewrites that happen. But once you've modified the state, is it possible that a rewrite that failed the precondition check could now be applicable? And do you go back through the rewrites, or once it fails the preconditions, that's
talking
it?
about the last section?
Mhm.
Yeah, so once it fails a precondition in that last section, it will always jump to another state. So it always exits. So when we're doing the compilation, there's only one path through that blue line. Pull this up so people follow. So there's only this one line through the rewrites, which is this blue line, and it always jumps off to some state down here. But these states, like state 32, can have more rewrites that come off of it. It's terrible.
But I mean, like, here it says like precondition test number 1 failed. So is state 32 then tried again on that?
Yeah, so state 32 will have its own rewrites generated for it. So state 32 will have so like in this case, you have state 10 goes through rewrite, it hits state 41, which has rewrites, and hits state 86 or 89.
Thanks.
I have a question about in your part 1, you mentioned something infinite rules.
Infinite rules? Yeah, so basically the quote unquote infinite rules are just that it's defined over an infinite set of values. So if you do
The difference between the normal Prolog rules, which should also apply on the possible facts. So what's the difference between the infinite rule and the normal rule?
So this is defined for all x, and this would be, so the normal way you would do this in Prolog is you would say, I'm calling a of x, and then somehow you would loop over the set of x values. So this is defined for all x, and that quote unquote makes it infinite. And this object is good. There's an infinite number of objects getting allocated because of because you don't have any sort of like this is just all floating point numbers.
I think the point is you could have an infinite number of objects allocated, quote unquote, in Prolog as well. I think what you want to claim here is that you don't have to iterate over them to aggregate over them because you might have some special rewrite rule that is able to aggregate over an infinite number of things.
Right. So you don't have so you can't have an infinite number of objects in Prolog, and it's conceptually the same as so the object system is basically prototype-based inheritance, and there's like a system called logtalk, which is kind of similar. It also does prototype inheritance in Prolog. And you can think of this object-oriented thing as sort of syntactic sugar on top of others.
Yeah, I don't think the infiniteness is really relevant. I mean, I think it's orthogonal to the infinitude. Yeah, I mean, you could certainly write like, A of X, Y. In Prolog, you could write A of X, Y if Y equals X minus 5 squared. And that's true of an infinite number of pairs.
Yeah,
So you can certainly write it down. I think what you were saying here is maybe you could aggregate over it with some rewrite
Right.
rules that know about math and they know how to minimize quadratic.
right. So the standard way, the way that aggregation is done in Prolog and Datalog is basically just put it in a list and then go through the list with your aggregator, right? And so that would be an infinitely long list. And assuming you have some sort of special handling for your aggregators, then you could conceptually handle this.
In the same way Mathematica would, for example,
Yeah,
when it could take an infinite sum and give you an actual answer without iterating because it has a rewrite.
yeah.
I have a question with regards to the rewriting part. So
Mhm.
have you looked into equality graphs and equality saturations? That type of work where they represent many equivalent programs in one p-type graph?
I have not reviewed that work recently.
Because that's another popular way to drive rewrite-based systems, compiler
Yeah,
optimization.
I mean, so our rewrite system is, what we've done. I don't claim that that part is particularly novel. I mean, people have rewrite, we have rewrite, rewrites are everywhere, they're great. Our thing is, one reason that we ended up building our own was that we wanted to be a bit more non-deterministic than a lot of the other systems were. They would say like, here's a tree and only matches the root. And we were just like, here's a big tree, go search through the whole thing. So that was a little bit weird from a lot of the other sort of, not math side, but like implementation side of rewrite systems.
When you say tree, actually, you mean the abstract syntax tree of your program.
Yeah, the RX, it's a tree data structure. It's a recursive tree data structure.
I'm just curious as that some of the real rewrites in compilers that will be easily applicable on IR level. I don't know whether.
Yeah, I mean, the RXpers are essentially our IR. Yeah, so I think compilers will do rewrites. I mean, I even make this point at some point in the dissertation that in some sense our rewrite system is like a optimizing compiler on the internal AST of where the AST is the internal representation is the RXper.
We all ask other questions. if you have-
More questions from the Zoom crowd? Don't be shy.
So one thing I don't understand is sort of what happens when you give it things that it's not going to figure out. Seems like it's not going to terminate where you might guess, but I'm not really quite clear. So one example is, and maybe this isn't even well formed, but suppose you have like your Fibonacci function and you asked, is Fibonacci of X always greater than or equal to 0? Quick question. So it's basically it's basically a logic question. And we actually, this Robert and I in our research actually use Z3 to solve these kind of questions. That's why I'm particularly curious.
Very similar to the question on the screen, actually, which is minimizing over an infinite set. So you're doing an existential over an infinite or universal.
Right, yeah. You can do that, but I just wondered for that particular example, what it would do if you fed in something like that.
So if you fed in something like that, basically what will happen is it will. So I didn't get to this in the talk, but in the dissertation document, there's like a depth limit to prevent it from running forever.
Yeah.
Which once you bound the depth, then it will guarantee termination, but that doesn't guarantee a useful result.
Right, yeah. So it'll basically, it'll turn like,
You'll just get a big RX, which is
yeah.
expanded up to some depth
It stops there and dumps.
and you're just like, and then getting back an RX is not a happy feeling.
Yeah. Okay, thanks.
So Tim Vieira's dissertation, Tim, I think is on the call, or at least he was, does actually include static analysis that would enable you to determine that the Fibonacci's are always positive. But that's a separate question, I think, from being able to ask the query and have it generate that static analysis on the fly.
Yeah, and you could conceptually, you can keep adding rewrites. I have probably like 500 in the implementation right now. But like, I think, you know, there's no closed set of rewrites that's going to solve everything. So you can just keep adding to solve more problems. And I think if you think about a system like Mathematica, which is like also rewriting based and proof based, every release they're just adding rewrites and it can solve more and more stuff. And I think, you know, that could be a reasonable feature of Dino, just keep adding more and more stuff to the system to support more and more programs.
Is that actually, just to pick up on Scott's question, can you actually solve the issue of Fibonacci always being positive with a rewrite-based system? I mean, that seems to require analysis of the recursive user definition.
I mean, it would be like rewrites, including the definition, yeah. I mean, I didn't really, I mean, I talk about folding and unfolding a little bit in the dissertation document, which would be necessary for that. But
Yeah, that's rewriting a set of definitions is different from rewriting
rewriting
an expression, right? You don't have it. Other than the folding stuff, you don't have anything for that, I think.
That's right.
All right, well, last chance for questions from the audience.
Thanks for coming, everyone.
Thank you.
We excused.
You're excused, Calvin.
Takes food.
Oh, goodness.
Takes the food.
No.
Don't get to hear the juicy discussion.
Yeah,
Thank you.
is the room camera on? I don't see it in the camera. Remember, I turned it on, so.
Yeah, let me
See you walk around.
That's the podium.
Oh, yeah, it's on.
You should be able, if you're the host, you should be able
It's
to
on.
contact non-committee members.
Yeah, let me just, I'm trying.
White camera that might.
I will.
Actually, no, they're both good. Shows you. Whatever, no biggie.
Recording.